March 25th. NASA orders a total shutdown of the Buga experiment. No warning, no explanation. Just hours before, their scientists detected a surge so powerful it breached every safeguard, sending pulses that baffled anyone watching the monitors. The data log spiked, alarms blared, and then silence. What forced NASA's hand? Why did one anomaly inside a Colombian lab send shock waves through the world's top space agency? The stakes are higher than you think, and what happened inside that sealed room may never be revealed. But here's the real question. What did NASA see inside the Buga that made them pull the plug? At exactly 14:07 UTC, NASA's Mission Control issued the shutdown command. No debate, no hesitation. The order went out across secure channels, triggering a cascade of emergency protocols at the Buga research site. Every terminal inside the Colombian facility locked out within seconds. Researchers found themselves staring at frozen screens, their access revoked in real time. The experiment, once hailed as a model for international scientific collaboration, was now classified at the highest level. That morning, a digital memo circulated through NASA's internal system, stamped with the agency's highest clearance code. The subject line was blunt: immediate suspension, Buga protocol. Attached was a single line of sensor data, an energy spike so far beyond the lab's safety thresholds that it defied the automated kill switches. The timestamp on the memo matched the moment alarms began to overlap, each system logging a surge of unknown origin. The facility's lead scientist, Dr. Rafael Mendez, tried to override the lockdown. His credentials, valid minutes before, now returned a denial code reserved for national security emergencies. In the control room, the team watched as their experimental logs vanished from local storage, rerouted to a secure NASA archive. The only physical evidence left was the sphere itself, now sealed inside a reinforced containment vault. Calls to NASA headquarters in Houston were met with silence. The only response came in the form of a couriered envelope delivered by diplomatic escort, instructing Colombian authorities to restrict access to the site. The language was unambiguous. All data, samples, and personnel movements were now subject to direct oversight by NASA's Office of Planetary Protection. Within hours, rumors spread among the international researchers stationed at Buga. Some whispered about a classified experiment gone wrong. Others speculated about the nature of the anomaly, a pulse, a resonance, something that set off every warning system in the building. The only certainty was the abruptness of the shutdown and the scale of NASA's response. Consider this. The Buga had been under joint study for just 6 weeks when the shutdown order arrived. The project, once celebrated in academic circles, now existed only in redacted memos and encrypted backups. The experiment's status shifted from open research to total blackout in less than an hour. Yet, the real question lingered in every corridor and conference call. What did NASA's sensors register inside that sealed vault? Why invoke the highest level of security for an experiment thousands of miles from Cape Canaveral? And what, if anything, could force the world's most experienced space agency to pull the plug on its own breakthrough research? Without warning, without explanation, and with every indication that something had crossed the line no one was prepared to face. March 25th, just outside the city of Buga in Colombia, dawn breaks over a patchwork of farmland. But something new sits in the grass. A metallic sphere, smooth as glass, reflecting the morning sun. No scorch marks, no crater, just a perfect landing in the middle of a field. Local farmers gather, drawn by stories of light zigzagging across the sky hours earlier. They expect wreckage, maybe a fragment from an old satellite. Instead, they find a flawless orb, cold to the touch despite the tropical heat. The first to approach is Jose Restrepo, a coffee grower whose boots crunch over brittle grass. He presses his palm against the sphere. It's colder than ice but not frozen. He calls for help, and soon a crowd forms. Neighbors, farmhands, even the town's police chief. Someone brings a bathroom scale. The reading hovers just above 2 kilograms. A few minutes later, they try again. The number jumps. By noon, it weighs nearly 10. The group argues, but the numbers don't lie. Word spreads. By midday, The police cordon off the site and call for scientists from the nearest university. Students and professors arrive with tape measures and notebooks. They record the diameter, just under 30 centimeters, and note the absence of seams, welds, or any sign of assembly. The surface is flawless, as if the metal was cast in a single pour. A botanist kneels to examine the grass beneath the sphere. Every blade is wilted, gray, and brittle. The patch of dead vegetation forms a perfect ring, no more than a meter across. Soil samples are bagged. Some whisper about radiation, but the Geiger counter stays silent. A local journalist posts the first photos online. Within hours, the hashtag Bugosphere trends across Colombia. The images show villagers standing in a loose circle, staring at the object as if waiting for it to do something. The sphere remains silent, unmoving, and impossibly cold. By nightfall, the authorities make a decision. The sphere is loaded into a reinforced crate and transported under police escort to a university lab in Cali. Scientists from Bogotá and Medellín request access. International calls begin first to UNAM in Mexico, then to MIT Center for Materials Research. The object is no longer just a local curiosity. Back in the field, the circle of dead grass remains. Days later, nothing grows there. The soil is dry as dust, stripped of moisture. Local children dare each other to step inside the ring, but none linger. For the people of Buga, the field becomes a landmark, a place where something impossible touched down and left a mark no one can explain. The sphere's journey is just beginning. In the lab, new questions arise with every test. But the story of the Bugosphere starts here, in an ordinary field, with a group of witnesses and an object that defies every expectation. Lab technicians in Cali began with the basics: hardness, density, and structure. The first surprise came from the gyrometer. The sphere registered a hardness of 330, nearly double the rating for aerospace-grade aluminum. Standard alloys can't reach those numbers, not without additives or intense post-processing. Yet, chemical analysis revealed no known alloy mix, just an aluminum signature with trace elements that didn't match any terrestrial database. Surface scans revealed something even stranger. Under magnification, the sphere looked poured, not machined. No seams, rivets, or weld lines. The entire surface was continuous, as if the metal had been formed in one flawless motion. Even under electron microscopy, technicians found no grain boundaries or microfractures. It was as if the object had never been assembled, only created whole. Attempts to cut a microsample failed. Diamond-tipped tools dulled against the surface, leaving only faint scratches. When a carbide drill finally removed a sliver, the core mirrored the shell. Same hardness, same seamless structure. The sample's cross-section showed perfect uniformity. No layering, no composite fibers, nothing to suggest how it was made. Technicians ran density tests next. The numbers fluctuated, sometimes by as much as 15% between trials. The lab recalibrated their scales, checked for static, even swapped out the equipment, but the readings stayed inconsistent. The only constant was the sphere's resistance to every conventional test. Spectroscopy revealed trace elements: yttrium, vanadium, and a rare isotope of magnesium, none of them in concentrations seen in commercial alloys. One metallurgist joked it was like the periodic table had been rearranged just for this object. By the end of the first week, the team had a list of what the sphere wasn't. It wasn't cast, forged, or 3D printed. It wasn't a meteorite, satellite part, or industrial scrap. Every test pointed to a level of precision and control beyond any current manufacturing process. The absence of assembly marks or fabrication scars raised new questions. If the sphere wasn't made by any process known on Earth, what kind of technology could produce such a seamless, flawless object? Some researchers began to whisper about non-terrestrial origins, but the evidence was still locked inside. The next step was clear: internal imaging. Only a full scan could reveal what, if anything, lay beneath that perfect shell. But before the technicians could start, the sphere's presence had already begun to change the lab itself. The story of its impact on the site was only beginning. A month after the sphere left Buga, The grass inside the impact ring still had not come back. Soil samples pulled from the heart of that barren patch showed a total loss of moisture and a collapse in microbial life. One lab in Cali ran the numbers twice. The topsoil's organic content had dropped by 60% in just 3 weeks. No chemical residue, no trace of heat damage, just a perfect circle where nothing grew, as if the ground itself had been emptied out. Local farmers kept their distance. A few tried replanting beans and cassava, but every seedling withered before breaking the surface. Even weeds skirted the edge of the ring. The land, usually thick with insects and birds, fell silent. Only the wind moved through the dry stalks at the boundary. At night, the air inside the circle felt cooler, almost heavy, like the ground was pulling in the cold. Technicians from Universidad del Valle set up vibration sensors around the perimeter. On quiet mornings, the soil inside the ring hummed at a barely audible frequency. 2.3 hertz, repeating every few seconds. The readings matched the pulse some claimed to have measured in the lab. Though no one could explain why the vibration persisted long after the sphere was gone. The effect faded with distance, vanishing just outside the dead zone. Sound tests brought new questions. When researchers played a sweep of tones across the site, the ground responded only to a narrow band. At 2.1 hertz, sensors picked up a faint tremor. At higher frequencies, the soil stayed still. The pattern repeated day after day, always in the same range. One acoustics professor called it a tuning fork for the Earth, but no one could say what was vibrating or why it had started after the sphere's arrival. By early May, the land around the ring began to shift. A patch that once sloped gently toward the river now measured 3 centimeters lower than before. Satellite data confirmed a subtle depression, as if the ground had compacted under invisible weight. Engineers ruled out sinkholes and groundwater loss. The only change was the presence of that perfect, silent ring. The field became a magnet for researchers and skeptics alike. Some came hunting for radiation, others for exotic particles. None found answers. What remained was a patch of land stripped bare, a vibration no one could source, and a question that kept drawing new eyes. What kind of energy could hollow out the Earth and leave a permanent mark months after the sphere had moved on? The search for an explanation would soon turn inside, toward the sphere's core. The first internal images of the Buga stunned the team. High-resolution X-ray scans captured at the UNAM lab revealed a structure unlike anything in the existing materials database. 3 concentric shells, each perfectly spherical, nested one inside the next. The outer shell measured just under 30 centimeters across with uniform thickness down to the millimeter. No welds, no seams, no sign of how the layers were joined. Just a flawless metallic continuum from surface to core. Inside the middle shell, the scan picked up a striking pattern. 18 microspheres, each identical in size and density, positioned at precise intervals along an invisible lattice. The arrangement wasn't random. Imaging specialists overlaid geometric models and found the spheres matched a truncated icosahedral pattern. Think of the way carbon atoms bond in a buckyball, but on a much larger scale. Every microsphere hovered in its own cavity, suspended within the shell matrix with no visible supports holding them in place. Between the shells, the scan revealed a faint network of filaments thinner than a human hair, running in arcs and loops from one microsphere to another. The filaments appeared denser near the sphere's equator, forming a band that wrapped the entire circumference like a belt of woven light. The imaging software struggled to resolve their full detail, but early analysis suggested a regular spacing, each filament branching from a microsphere and converging at specific nodes along the inner shell. Technicians ran the scan again, this time increasing the energy to probe for denser materials. The core of the sphere responded with a sharp contrast spike, hinting at a central mass far denser than the shells or the surrounding microspheres. Some on the team speculated about a processing unit, others about a power source. The only consensus: the internal order was deliberate, engineered with a precision that left no room for chance. The ratio between the shells, microspheres, and filaments followed a mathematical progression. The outer shell's thickness measured exactly 1/6 of the sphere's radius. The microspheres were spaced at intervals that matched the golden ratio when measured from the core outward. Even the filament network showed repeating patterns, as if the entire structure had been designed to resonate at specific frequencies. Imaging specialists compared the scans to known aerospace and nanotech designs. Nothing matched. The closest analogs were theoretical diagrams from quantum computing journals, concepts, not hardware. The lab's lead analyst, Dr. Herrera, called it an information lattice, a physical embodiment of a code or algorithm. But the function remained a mystery. Was the array meant to store data, channel energy, or something else entirely? One thing was clear. This wasn't a natural formation, nor the product of any known industrial process. The sphere's internal order hinted at a purpose beyond simple construction. Every layer, every microsphere, every filament pointed to a system designed for interaction, not isolation. The next step would be to trace the filaments and decode their connections, hoping the answers wouldn't raise even deeper questions. Electrical engineers at the Cali lab started mapping the internal filaments. The first scans showed a web of ultra-thin fibers, each no thicker than a strand of silk, running in precise arcs between the microspheres and the core. These were not random inclusions or stress fractures. Under polarized light, the filaments bent and split beams, behaving like high-grade optical fibers. Except these were embedded in solid metal, not glass. Material analysis revealed traces of yttrium and vanadium elements used in advanced photonics and superconductors, woven into the aluminum matrix. At the equator, the fibers converged in a dense ring, forming what looked almost like a data bus on a computer chip. Engineers traced the paths from the outer shell through the microspheres and into a compact node at the very center. That node registered as the highest density region in the entire scan. It was surrounded by a cluster of copper contacts, each precisely spaced as if designed for direct electrical connection, yet sealed inside a shell that nothing could penetrate. Some on the team compared the layout to the backplane of a supercomputer or the nervous system of a living organism. The density of connections in the equatorial band far exceeded anything seen in terrestrial electronics. One engineer, after running the numbers, calculated the potential bandwidth, trillions of bits per second, if the fibers really functioned as optical channels. But there was no sign of a power source, no external ports, no evidence of conventional circuitry. The more the team probed, the less inert the sphere appeared. Every filament, every node, every copper contact suggested an active system, something built to transmit, process, or maybe even emit energy. The core's composition defied simple explanation. Spectroscopy hinted at doped polymers and rare earth alloys, materials used in quantum sensors and next-generation chips. The arrangement was too deliberate for a relic, too complex for a passive artifact. One question kept coming up in the control room. If this was just a shell, why invest so much in a hidden network? Why build a lattice that could move light or signals with such precision only to bury it inside a sealed sphere? The team's working theory shifted. Maybe the sphere was not just a container. Maybe it was designed to do something that required a network capable of channeling energy or information at a scale no one expected. The next round of tests would push the system, looking for any sign that the fibers could carry a signal or unleash something even stranger. At 14:09 UTC, a technician in the shielded control room noticed something no one could explain. The sphere's internal sensors had started logging a rhythmic electromagnetic emission, steady, repeating, and far below the range of normal laboratory interference. The frequency, 2.13 Hz. That number didn't match any known background noise, nor did it correspond to the building's power grid, seismic activity, or even the Schumann resonance. The team checked the spectrum analyzer twice. The pulse was crisp, almost mechanical, a perfect heartbeat, repeating every 470 milliseconds. The lab's Faraday cage, designed to block even the faintest electromagnetic signals, offered no protection. The pulse registered at full amplitude both inside and outside the enclosure. Shielded equipment racks, triple-layered new metal barriers, even the backup generator's isolated ground, all of it useless. Every sensor in the building picked up the same pattern, as if the signal ignored the laws of physics. One engineer ran a diagnostic on the spectrum analyzer, suspecting a calibration fault. The test returned clean. The emission was real and it was everywhere. Within minutes, the anomaly crossed a threshold that forced the team to escalate. The pulse began to drift, modulating in amplitude and overlapping with the 2.4 Hz band used by military communication systems. For a brief window, the signal's harmonic brushed against the encrypted channel reserved for base security. The overlap triggered a secondary alarm. Protocol demanded a full electromagnetic sweep and immediate notification of the site's director. What started as a strange lab reading now risked interfering with secure communications across the entire facility. The lead sensor specialist, Dr. Elena Ruiz, pulled up the wave propagation data. The pulse radiated outward from the sphere's center in perfect concentric shells, unaffected by concrete, steel, or copper mesh. The readings showed the field strength didn't drop off with distance the way normal electromagnetic waves do. Instead, it maintained a constant amplitude for nearly 30 meters before fading into background noise. Ruiz ran the numbers again. The emission had a propagation profile more like a submarine ELF transmitter than any lab equipment. But this was a sealed object, not an antenna array. Attempts to dampen the pulse with active countermeasures failed. White noise generators, phase-canceling signals, even direct grounding, all had no effect. The field cut through every barrier as if the sphere and its emission existed in a different layer of reality. The only thing that changed was the room's temperature. Within an hour, the ambient air dropped by nearly 6 degrees Celsius, and the cooling system struggled to compensate. The correlation between the pulse and the sudden energy drain was impossible to ignore. Ruiz and her team documented every cycle, every spike, every moment the field shifted. The log showed a precision that bordered on intentional. The pulse seemed to adapt, shifting slightly each time a new countermeasure was activated. At 2.13 Hz, the frequency sat just above the threshold for human perception. Too low to hear, too deep to feel, but strong enough to register on every instrument in the lab. The overlap with restricted military bands raised a new concern. If the pulse could bypass electromagnetic shielding, what else could it reach? The team's final report flagged the anomaly as unprecedented. No known material, device, or natural phenomenon could account for a signal with this frequency, amplitude, and ability to penetrate barriers. The only constant was its origin. The heart of the Bugosphere, sealed behind layers of metal and mystery. But as the field continued to pulse, one question kept repeating, just like the signal itself. What was the sphere trying to reach? At 1411 UTC, the facility's main power log spiked. Cooling units, already running at maximum, began drawing an extra 100 watts, far above baseline. The temperature in the containment vault dropped by 4 degrees in under 3 minutes. Engineers scrambled to reroute power, but the sphere's demand kept climbing. Every subsystem tied to environmental regulation showed the same pattern. A sudden, synchronized drain that pulled energy from the grid faster than backup systems could compensate. Internal logs captured the anomaly in real time. The cooling loop, designed to stabilize the chamber at -10 degrees Celsius, now registered a negative gradient the system had never recorded. The sphere was absorbing heat at a rate that outpaced the lab's entire thermal budget. No chemical reaction, no phase change, just a relentless extraction of energy. Instrumentation flagged the event as endothermic. 100 watts sustained with no corresponding output. The system's safety margins collapsed. Lab Director Dr. Rafael Mendez authorized a hard shutdown. The order was timestamped 1412:17 UTC. Within seconds, breakers tripped across the experimental wing, isolating the sphere from every electrical and cooling supply. Emergency batteries kicked in, but the draw continued, now leaching residual energy from the room's ambient air. The temperature kept falling. Frost formed on the outer shell of the containment vault. Technicians watched the sphere's energy profile flatten, then spike again, this time in reverse. The cooling graph showed a sudden plateau, as if the object had reached equilibrium and stopped drawing heat. The event lasted just under 4 minutes. When the vault was finally unsealed, the air inside was dense and biting cold. Condensation dripped from every metal surface. The sphere itself, still sealed behind 3 layers of shielding, registered at -28 degrees Celsius. Facility power logs, reviewed later, confirmed the numbers. A 100-watt endothermic event sustained longer than any test on record. No external trigger, no known mechanism, just a silent, perfect absorption of energy. The data left no room for doubt. Whatever the sphere was doing, it was active, and it had forced the lab past every safety threshold. The decision to halt the experiment wasn't just protocol. It was the only option left. But the aftermath brought new questions. What kind of system could pull that much energy without warning? And what would happen if the sphere was left unchecked? Still hungry for more, physicists across 3 continents started running models as soon as the sensor logs went public. The numbers did not fit anything in the standard playbook. The pulse, repeating at 2.13 Hz, landed well below the Schumann resonance, the natural electromagnetic heartbeat of the planet, which hums at 7.83 Hz. That baseline, measured for decades, is so stable it's used to calibrate sensitive equipment around the world. Yet the Bugasphere's emission sat at a frequency that should not resonate with anything in Earth's environment. The closest analog, according to a team at MIT, would be the way a tuning fork vibrates, not at the note you expect, but at a subharmonic so low it slips beneath human hearing. Some researchers turned to quantum sensing for answers. The sphere's internal filaments, laced with yttrium and vanadium, match the materials found in state-of-the-art quantum gravimeters, devices designed to pick up the faintest ripples in the planet's magnetic field. These sensors, when cooled to near absolute zero, can detect shifts as subtle as a passing truck or a distant thunderstorm. But the Bugasphere's readings were different. The emission was not a reaction to outside changes. It was self-generated, stable, and immune to the usual noise that plagues even the best quantum instruments. One theory proposed the sphere was acting as a kind of planetary stethoscope, tuned to frequencies that bypass normal interference. If true, it would mean the object could sense, maybe even influence, resonance patterns deep inside the Earth. The implications go beyond academic curiosity. If a device can interact with the planet's natural frequencies, it could, in theory, affect everything from animal migration to regional weather. And if the 2.13 Hz anomaly was more than just a byproduct, but an intentional signal, the stakes for understanding its purpose just multiplied. The debate now turned to the sphere's true function. Was it a passive recorder, a quantum sensor designed to map the world's hidden rhythms? Or was it something more active, capable of generating resonance that could ripple through the planet's electromagnetic fabric? The only certainty came from the data itself. No known material, no terrestrial technology, and no accidental process could account for a signal this precise, this persistent, or this deeply woven into the natural frequencies of the Earth. The search for a mechanism was just beginning. Grid engineers in Bogota reviewed the logs 3 times. The numbers matched the lab's. A 2.1 Hz pulse, faint but steady, riding the city's power lines. For 20 minutes, substations across the valley registered microsurges. Too small to trip breakers, but enough to trigger diagnostic alerts. None of the usual culprits fit. No thunderstorms, no solar flares, no industrial load spikes. The pattern repeated in Cali and Medellin, always in sync with the Bugasphere's last recorded emission. This wasn't just a lab curiosity. The same frequency, just above the floor of human perception, falls squarely into the band used for submarine communications and deep Earth transmission. In the 1970s, the U.S. Navy spent billions to broadcast at 76 Hz. Here, a sealed metallic sphere in Colombia was radiating a signal 30 times lower, and nothing, not steel, not copper mesh, not concrete, could block it. Researchers at the Universidad Nacional ran simulations. If a pulse like this were amplified even by a few orders of magnitude, it could resonate with the grid's long-haul transmission lines. The risk isn't science fiction. In 1989, a geomagnetic storm tripped the entire Hydro-Quebec network, plunging 6 million people into darkness. That event started with a natural magnetic pulse, nowhere near as precise as what Buga's sensors recorded. The unanswered question: what happens if a device, deliberate or not, can inject energy at exactly the right frequency to ride the backbone of a modern power grid? Some engineers point to ELF interference studies, warning that harmonics in this range can bypass standard filters, destabilize transformers, and ripple through entire regions before anyone can react. The Bugasphere's field faded before it reached that threshold. But the precedent is there. Every blackout, every unexplained surge, every unexplained field event. These are the cracks in the system that keep grid operators up at night. The Bugasphere's anomaly isn't just an academic puzzle. It's a warning. The world's infrastructure is built on assumptions about what can and can't happen. When those assumptions fail, the consequences aren't local. They're global. No one at NASA or the Colombian Ministry of Energy will say it out loud. But the silence, the classified memos, the sudden lockdowns, they all point to the same reality. Whatever the sphere was doing, it reached beyond the lab. And the next time a pulse like that appears, the world may not get a warning at all. On March 18, 2025, NASA confirmed the abrupt shutdown of the Bugasphere experiment after lab sensors recorded an unexplained electromagnetic pulse at 2.2 Hz. X-ray imaging revealed an engineered interior, 3 concentric shells, 18 microspheres, and a dense fiber network, all with properties no known alloy could match. Field tests showed vegetation die-off and persistent acoustic anomalies, while power logs documented a 100-watt cooling event during the anomaly. To date, NASA has released only partial findings, and over 60% of technical files remain classified. Independent experts from UNAM and MIT agree the sphere's structure suggests advanced design, but its true purpose is still unknown. The electromagnetic pulse, which breached all shielding, raises real concerns about grid vulnerability and planetary resonance. What is certain is this: NASA's decision to halt the experiment was based on direct evidence and documented risk. As of today, the Bugasphere remains locked away, its secrets and the potential impact on our world still unanswered.